Bismillahirrahmanirrahim. In this lecture, we discuss about the Ehrenfest theorem. In quantum mechanics, is to be more general than the classical. If the quantum mechanics is to be more general than the classical mechanics, it must contain the classical mechanics as a limiting case. What it means? It means the connection between the quantum and the classical mechanics is h bar or h. This is a Planck constant or the Dirac constant. When the Planck constant approaches to zero, then we can connect the quantum mechanics to the classical mechanics. It means when h disappears, then quantum mechanics reach to the limit of classical mechanics. To illustrate this idea, let us look at the time evolution of expectation value of the position and the momentum operator. This is a position operator, and here is the momentum operator of a particle moving in a potential VR. And then we compare the relation between the quantum mechanics and the classical mechanics for the position and for the momentum. Since the position and momentum observable, these both, the position and the momentum, these both does not explicitly on time. It means partial r over partial t, and then we take the average of this. This is just the average of the velocity, and this is the average of the force. Both are going to zero because these observable does not depend explicitly on time. And then this is the Hamiltonian, and Hamiltonian is just the kinetic energy part, p square over 2m plus v, the potential energy. We're using this Hamiltonian, and we are also claiming R commute with v. Then according to the equation 3.88 that we have already discussed, then d over dt over the average position is equal to 1 over iota h bar, and then average, and in commuting bracket we have r and h. The same as we have done already in equation 3.88. Now this h can be expanded into the kinetic energy plus the potential energy. It means this r will commute with this kinetic energy and r will commute with this potential energy. If r commute with the potential energy, then this factor goes to 0. The remaining term is 1 over 2 iota m h bar, and average value, and in square bracket we can write position operator and the momentum square operator. Now this d over dt is just the velocity, and this velocity multiply this mass, then we can obtain this momentum operator. Means here our position operator and the momentum square operator is equal to 2 iota h bar p. And we have also this relation, the very, very simple, just the velocity or d over dt, average value of the position, is equal to 1 over m p average. Now, we have also inferred this relation that if momentum and the momentum and the potential energy, if both commute each other, then we have this relation. How? This just, we can write d over dt. This is the change in momentum, and this is equal to the 1 over iota h bar p and v in both. Here we can write from this equation, and then this is the force. As you know in earlier classes, force is the negative gradient of potential. Force is the negative gradient of potential energy. And these two relations this one and the relation this one means relation for the velocity and relation for the force. And here we can say the time evaluation of expectation values of both position and the momentum operator are known as Ehrenfest theorem. Ehrenfest theorem in classical mechanics, we have these type of equations. Velocity is equal to momentum divided by mass, and the force is negative gradient of potential energy, and this type of relation according to Newton second law. Here in both equations, 3.132 and 3.134, h bar is completely disappeared. It means classical limit is attained. Wave packet moving like a classical particle when subject to the potential VR. Here, just after finishing this topic, if you're facing any difficulties or to solve these things, you can do it's very simple mathematics. Just you can compute PV minus VP and use an index function, and then apply some operators, then we can get this value. And similarly, you can also prove this.